Okay, good morning, everybody. Thank you very much for joining us this morning. My name's David Reid. I'm one of the mechanical and electrical design engineers at Mesh Energy. And this morning, I'm going to give you a very quick whistle-stop tour through air source heat pumps and through some of the things that you need to think about when you're designing a building with an air source heat pump, and also some of the little sort of bits around how to best optimize an air source heat pump system. We're going to start from the very basics and try and work through to some slightly more advanced stuff. If at any point you have any questions, please tap them into the comments box, and we'll pick them up at the end. And we'll, without further ado, the only other thing I'd ask is just from a housekeeping point of view, if I can ask you please just to keep your microphones muted, just because it can get a bit irritating if a dog starts barking or something in the background. Okay, let's crack on. So it's a quick run through of what we're going to cover today. So brief introduction, a little bit about Mesh Energy, what an air source heat pump is, and then some basic theory about how air source heat pumps actually work and how they put heat into a building, and then a little bit about some of the myths that surround air source heat pumps and their applications, and just to dispel a few of those myths. Then we're going to go on to a section around specification and design. So starting with probably the most important one, which is making sure you get planning permission if required and where permitted development can be used. Sizing and heat demands. A little bit about space considerations. So how much space do we actually need to allow both internally and externally for the installation. A little bit about underfloor heating, radiators, and then some bits around some of the sort of ancillary bits, so noise, the electrical supply, because obviously heat pumps run off electricity, so we need to make sure there's enough electricity there to power them. And then finally, one that people sometimes forget about, which is condensate, because air source heat pumps, the external units do produce a bit of condensate, and that's quite cold water, so it needs to be dealt with appropriately. Then we're going to go on to a little bit about the three subsidy packages that are available at the moment, which are the domestic and non-domestic renewable heat incentive, and the new one, the new kid on the block, which is the Green Home Grant. And then finally, we'll conclude with a little bit about the next steps. So this is the key points of what, sort of key takeaways, and then how we can partner together to deliver on your projects. So hopefully, as you can see, there's quite a lot to get through today. If you feel I'm going too fast, as I say, please ask questions. I will try and keep the sort of the level to somewhere that's sort of appropriate. Obviously, if there's I can't cover every single piece of technical information in this one PowerPoint presentation. If I tried to, it would frankly become unmanageable, both for me and for you guys. So I will try and cover the basics, and then obviously if you've got any more specific questions, please ask. Okay, so just start with a little bit about who Mesh Energy are. I'm sure an awful lot of you will have heard this and seen this slide lots of times. We're an award-winning independent energy consultancy based in Farnham in Surrey, and what we try to do is we try to simplify the sustainable energy landscape. So there's lots of competing technologies. Lots of them work in potentially work very well together. Some of them less so. But what we try and do is we try and remain holistic and impartial with our advice. So we're not tied to any particular manufacturers. We're not tied to any particular technology. We will always try and specify the best solution for a particular project. So that's really what we aim to do, and that can start all the way from sort of a very early stage feasibility study, when the building might just be a few lines on a piece of paper, all the way through to post-occupancy evaluation and monitoring, and making sure that the system's actually optimized and performing at its best. So let's start with the very basics. What is an air source heat pump? Well, it is basically an electrically powered device which takes low-grade heat from the environment and turns it into high-grade heat that you can use for space heating, domestic hot water heating, and heating a swimming pool. So here's a sort of very basic diagram showing an air source heat pump, and it's showing that warm air is being taken in through one side of the heat pump and cold air is being pushed out the other side. And when we say warm, we're talking about any air that's got energy in it. So it doesn't need to be warm as you or I might perceive warmth. It could be air that's as cold as -15, -20 degrees C. There's still useful energy in that air. It uses electricity to power the refrigeration cycle. And as I say, it can provide space heating, domestic hot water, and swimming pool heating. So they're quite a flexible piece of kit. I'd like to say they're a direct replacement for a boiler. They're not quite a direct replacement for a boiler, but we'll look at that in a little bit more detail in the specification section. And the other thing you'll hear me talk about quite a lot during this is something called the coefficient of performance. And if coefficient of performance and efficiency are really one and the same thing. You can't really say that a heat pump has an efficiency, because an efficiency by definition must be less than 100%. And the coefficient of performance for a heat pump is typically between 250 and 400%, or a COP of 2.5 to 4. So what that means is that for every kilowatt hour of electricity you put into the unit, you get between 2.5 kilowatt hours and 4 kilowatt hours of heat out of the unit. And there are lots of things you can do with the design to influence where you sit on that scale. And typically, always, the higher the number, the better the performance. So if you've got a COP of 4, that's really, really good. A COP of 2.5 is still, you're still getting 2.5 times as much heat out of a kilowatt hour of electricity as you would be with an electric sort of conventional electric heater. But it's not quite as good as it could be. And then the last sort of bit is that this outside fan unit is where you collect the energy, and that is sort of the common piece of pretty much all air source heat pump installations. There, I say an outdoor fan unit. I have seen a very small number of internal air source units where there's actually grills on the outside of the building, and you take air from outside through a heat pump that's inside the building and back out again. But the vast majority, probably 98% plus, use an outdoor fan unit. So we'll look at those in a little bit more detail and some of the choices around there. So how does a heat pump work? Well, basically it's based on a refrigeration cycle, same as the refrigeration cycle in your fridge in your kitchen. And all it does is it takes low-grade heat from one area. So if that was your fridge in your kitchen, that would be the box inside your fridge. And it passes it through a refrigeration cycle to turn it into high-grade heat that can then be used in the house. And if that was your fridge in your kitchen, that would be the black bars that you see on the back of your fridge internally. And the refrigeration cycle has 4 major components. It's starting from the compressor at the top here. That takes a low temperature gas at low pressure and pressurizes it, turning it into a high temperature, high pressure gas. That then goes through a condenser where it's turned into a high pressure liquid, and a lot of heat is rejected, which is what you're using to heat your home. That liquid, that low pressure gas is then that's then taken through the expansion valve, where it's turned back into a liquid, goes back into the evaporator. That's where it collects the heat externally. So at that point, you're talking about the temperature being significantly below freezing. and that gas then goes back, that then turns it back into a gas, which then goes back through the compressor, and the whole thing goes around again. So the refrigeration cycle is a sealed cycle. That refrigerant goes round and round and round, and the electrical input is in the compressor. Everything else is just a passive thing. The expansion valve is controlled, but that's how it works. So we'll just look at a little bit more detail there. So low-grade heat is harvested through the evaporator. Compressor raises the temperature and pressure of the refrigerant. Heat is transferred through the condenser, and then it's and then the expansion valve operates to get back to the start again. So it's pretty straightforward. It's a well-proven technology. There are thousands and thousands and thousands and thousands of millions of refrigerators around the world, loads of air conditioning units, which are pretty much the same thing operating the other way around. So it's a well-proven technology. There's nothing to be scared of, to be worried about with it. So let's have a look at a few of the myths around air source heat pumps, because these are the things that tend to put people off using them. And as I say, most of them are myths. So myth number one is they are really noisy. Air source heat pumps aren't really noisy, and we'll look at some of the reasons why an installation may become noisy if it's poorly designed, but the actual heat pumps themselves are not noisy. Secondly, they don't work properly in cold weather. Again, that's a bit of a myth. People think that you need to have a heat source, but they forget that heat is anything that's warmer than minus 273 degrees Celsius or 0 Kelvin. So even at minus 25 degrees ambient temperature, there is plenty of warmth in the air. It's just a question of extracting that heat. So you can make an air source heat pump work well in cold weather. They're used in northern Sweden and all kinds of places. It does work. The fan units have to go on the roof or near the house or building. Again, not always true, and we'll look at some ways of working around that. It is true that for a monoblock unit, it's best going near the building, but it's not absolutely necessary. The fourth myth is they can't do hot water. Again, that's simply not true. And you'll see that most of the modern heat pumps now will do a flow temperature which allows hot water to be stored at up to about 60 degrees C without any problem. Issues tend to come about when you have poor installations, and that's where that myth comes from. And the final one is that they don't work with radiators, and again, that is not true. But if you have a well-designed radiator system, an air source heat pump will work perfectly happily. Good. Right, so we've got the myths out of the way. Let's start with some of the more interesting stuff, some of the actual spec and design. So I'm sorry if I've kind of rushed through that a little bit. I'm hoping that an awful lot of people who are listening to this already have some of that background knowledge. So I was wanting to skip through it quite quickly. Obviously, if you've got any questions, please feel free to shout, and we'll do our best to answer them. So spec and design. So if we start by looking at planning permission, certainly in England, almost all heat pumps are a domestic size are installed under permitted development. There are a few things that you have to meet to qualify for that. First of all, that the heat pump complies with the microgeneration certification planning standards, which is MCS 020 or equivalent. Any decent heat pump installer should be able to make sure that that's done. It must be the only air source heat pump or wind turbine on the property. This is a fairly simple one to comply with in most cases. This is to avoid loads and loads of heat pumps being installed on one property. Lots of small, single room heat pumps that then potentially could cause a noise issue, because obviously the noise would then be sort of added together. Installations on flat roofs must be at least 1 meter from the edge of the roof. That's more of an aesthetic thing more than anything else, but again, pretty easy to comply with. and the air source heat pump must be used solely for heating. A lot of air source heat pumps are reversible, so if you want to do heating and cooling from your air source heat pump, then that's fine, but you'll probably have to go through planning. And the final one is another noise one, because there have been occasions where people have complained about noise coming from an air source heat pump in their neighbour's garden. You must be at least 1 metre from the boundary in order to avoid having to go through planning. Again, if you do have to go through planning, it's generally not a massive issue. And then they put an external unit volume sort of limit, again, just to sort of stop people putting massive commercial heat pumps into domestic properties, which would obviously be they're going to be bigger, noisier, more unsightly, etc. So that's why that last condition's there. So let's have a quick look at the space requirements for the outdoor unit. So as I said, in a lot of installations, or almost all installations, you're going to have the outdoor unit, and that may or may not be paired with an indoor unit. So let's have a look at some space considerations. So here's a sort of cutaway of a fairly typical sort of 3 or 4 bed home, and you can see down at the front corner here you've got your outdoor unit on a side wall away from bedrooms. It's not going to be obtrusive there. It's not sitting around any kind of living areas. As a rough rule of thumb, probably allow a couple of meters by a couple of meters for the footprint. You can see it's located away from social areas and bedroom windows, so you might have a patio around the back there. Probably not best to put your air source heat pump on the patio. Again, probably not best to put it right by the front door there. And there's no bedroom windows that overlook it. It's not right next to a bedroom window where potentially you could find it's a noise nuisance. Put it as close as possible to the plant room. Probably a good idea. Again, here we've got most of the planters up in this bathroom here. For the internal units, that's the domestic hot water cylinder. And the other thing is to avoid frost hollows. So a frost hollow would be an area where you didn't have good air circulation. So you want somewhere where air is sort of can freely get to that outside unit without being trapped in one place. So a really typical sort of place that people might try and put an air source heat pump without considering this would be a courtyard. And the issue with the courtyard is, especially if it's closed on all 4 sides, is that the air source heat pump will cool the air that goes through it, because it's taking that heat out to turn into high grade heat to heat the home. And obviously in a courtyard, that cold air will then tend to sink down into the bottom of the courtyard, at which point it will then get caught by the heat pump again and be cooled even more, and then it sinks even more, and you end up with this vicious cycle where the air just sort of collects, and it not only means that your courtyard becomes very cold, but it also damages the performance of the heat pump, and you end up with having to run more defrost cycles and all kinds of other issues, and it also hurts the actual efficiency of the heat pump system. So that's why that is there. The next one is avoid debris traps. It can be quite tempting to put a heat pump into a nice sort of neat corner by the garage, but especially if you've got broadleaf trees around, those areas can become sort of debris traps, and the last thing you want to be doing is sort of sucking lots of leaves and things into your heat pump, where they could block the evaporator coils. Just bear with me, I'm just going to take a sip of drink. Okay. And finally, avoid footpaths, doorways, and areas where the cold air coming out of the heat pump could be a nuisance. And the reason for that is twofold. One of which is it's not actually very nice to get a blast of cold air around your legs as you come out through your front door in the morning. But the second reason is that obviously that cold air does make it more likely there'll be frost forming in those areas, and obviously you don't want to have icy paths and things where they could become a trip hazard. And that adds on to this thing about the condensate drainage. we'll look at this in a bit more detail further on, but the volume of condensate that a heat pump will produce, especially in the relatively mild and damp climate we have in the UK, means that there will be a fair amount of condensate. That condensate has to go somewhere. What you don't want is for that condensate to run over a path, because it will be quite cold water and therefore could freeze potentially in the winter, and again create a trip hazard. So you can see here that we've tucked our external unit down the side of the house. It's well out of the way. It's not near any windows. It's not near any sort of social or living areas. Not near any paths. It's a great little location for it. You see, there's a little bit of planting next to it, and it's got a little soakaway underneath the base there, so allow for the condensate drainage. So good installation. Okay, so let's have a look at a monoblock system. So a monoblock system is where effectively the entire refrigeration cycle is contained in this external unit. This means that the pipes coming out of the unit contain water and not refrigerant. And the advantage of this type of system is twofold. One of which is it reduces the amount of internal plant you need, which saves space in the house. And the second thing is that because there's no refrigerant lines being run, that entire refrigeration cycle can be hermetically sealed in the factory, and that means you don't have to have F-gas qualifications to install this type of heat pump. So a good plumber who's been properly trained should be able to set this up and install it without having specialist qualifications. Disadvantages: this external unit will be slightly larger because it's got the extra gubbins in it for the condenser and for pumps and things. So it will be a slightly bigger external unit. So if you're limited for outside space, that might not be the best unit. The other thing to note is that because it's hot water running between the heat pump and the house, you can't site a monoblock quite as far away from the home as you can with a split system. So I'd probably say limit it to around 20 meters at the most from the house. So still a reasonable distance, and certainly more than enough to deal with any noise issues. But some people do like to tuck their heat pump right down the far end of the garden. So domestic hot water cylinders, you will always need a domestic hot water cylinder with a heat pump. There's no such thing as a sort of combi boiler equivalent for a heat pump. And typically that cylinder will be a little bit larger than for a conventional gas boiler. So you just need to take that into account. So here's our external units. That's contains all the pumps, etc. You'll see I've used the same diagram for all these. The water pipe work runs into the house, and your domestic hot water cylinder and distribution pipe work is all in that box in the bathroom in this case. So this is a sort of nice, neat, fairly typical monoblock installation. And I would say that monoblocks are probably the more common type of installations, especially on, for want of a better word, average houses. So your sort of 3-4 bed detached house and smaller. I think a monoblock system is probably going to be most suitable in most cases. So let's have a look at a split system. I'm going to use the same diagram again, just because people are sort of familiar with where things are, but we'll highlight some of the differences. So with a split system, you'd have to have an internal unit as well as an external unit, and that internal unit can be packaged in lots of different ways. But probably the most common way that it's packaged is in a sort of box that is roughly the same size as a conventional gas boiler. So if you're doing a retrofit, that can work quite well, because you take the boiler out, you put the internal unit for the air source heat pump into the same space. It looks fairly similar. You've got a couple of extra pipes coming into it. So instead of having a gas supply in there, you've got a refrigerant flow and return pipe going into it, and that contains the condenser and things like the water circulation pumps and heat exchangers and things like that. So that's what's inside that box. outside, you have a slightly smaller external unit. Domestic hot water cylinder wise, you have the same hot water cylinder as you had for your monoblock system. And what you can do is you can combine those two units together into a single unit, which they call a tower split unit. And what typically you then have is you have the hot water cylinder at the bottom, and then the condenser and the circulation pumps and things in a space in the top. So that's what a tower split unit is. And you can see what I'm trying to represent here with this diagram is a tower split unit. So everything goes into a central point. Disadvantage of tower split units is they can be quite tall, so they're not brilliant for sort of understairs cupboards. Quite often they won't fit, and they do tend to be a little bit more expensive than having two separate units. So here we are. Here's our external split unit. One of the advantages of a split unit is it can go. There's this external unit because you're running refrigerant lines to it rather than water lines. Heat loss along that length of pipe work is slightly less of an issue. So you can put that up to about 50 meters away from the house. So we quite often find these are useful in very high-end residential where they've got a lot of land. People sort of tuck that evaporator unit well away from the house, or up on a roof or somewhere where it's really discreet. And here's our refrigerant pipe work. So this does need an F-gas qualification to install. You can't just get your normal plumber to install this. They do have to have some specialist qualifications. And then here we've got a tower split unit where the domestic hot water cylinder and internal air source heat pump are a single unit. Okay, so there's a sort of two basic heat pump sort of models. So you've got your split unit and you've got your monoblock unit. So monoblock unit, very simple, everything's in the box. Split unit, you've got two boxes, and you've got refrigerant pipe work linking the two together. So what about sizing and heat demand? Well, let's start from our little mesh thing. You've probably seen this lots of times before. This is the sort of triangle of priorities. So what can we do to reduce energy consumption in a building? And what we'll do is we'll start from the very top here and we'll work down. So we'll follow this energy hierarchy. And what can we do to viably and economically improve the fabric of the building first? So when we talk about any renewable technology, we'll always start from, can we improve the building before we start throwing technology at it? It is always better to have a well-designed, well-insulated, airtight building before we start trying to lever good technologies into it. And that is for lots of reasons. One of which is that it's often a lot cheaper to insulate a building well than it is to try and heat a poorly insulated building with an advanced technology. So here's our typical house, and this is so we've made all the insulation upgrades we can. We've thought about where all the plant's going to go. We've decided we've sort of started doing some design for it. We've decided where it's going to go on the plot. If it's new build, obviously retrofit, we can't viably sort of move a house around to make it orientate more successfly. But here's a sort of quick rundown of how we would do the design. So we'd start by determining the design temperature, and the design temperature is simply a lookup of based on where the house is located and the elevation of the house above sea level. Then we'd look at what the best on most likely heating water flow temperature is going to be. And that's going to be determined from the type of heating system that we're looking to install. So if we've got an underfloor heating system and we've got a well-insulated building, we might be able to get that heating water flow temperature down to as low as 35 degrees C. With radiators, you're probably more likely going to be nearer the 50 degrees C mark. And And if you're retrofitting, it's more likely you're going to have to start looking at higher flow temperatures, simply because it's going to be more difficult to improve the fabric of the building. But as I said before, if you can improve the fabric of the building, potentially we can start dragging this heating water flow temperature down, and that then gives you a direct advantage on the COP of the heat pump. We're then going to determine the peak space heating load based on standard design room temperatures. So I'm sure we're all fairly familiar with that, but basically it's 21 degrees for living rooms, dining rooms, those kind of things. 18 degrees for bedrooms, kitchens, WCs, 22 for bathrooms, and then you can sort of adjust from there a little bit depending on client preference, etc. But we can get a pretty good idea of what the space heating demand is going to be, and that is obviously based on that design temperature that we've determined in step 1, and that tells us how much heat we're going to be losing on the worst day of the year, and that's where we go from there. Then we need to add a little bit onto that, because we're obviously going to be doing some hot water as well, and a good sort of rule of thumb is it's around 200 watts per person based on peak occupancy. And peak occupancy is usually determined by counting the number of bedrooms and adding 1, because you assume that you're going to have 2 people in the master bedroom and then 1 person in each subsequent bedroom from there, and that gives you a pretty good idea of what your domestic hot water load is going to be. And then we match the heat pump to those peak demands at design temperature, so we're not oversizing a heat pump, and this is quite important. With a gas boiler, you would probably oversize by maybe 50% over this peak demand. With a heat pump, you really don't want to be doing that. The cost, both the installation, potential electrical upgrades, everything else, means that you really want to match the heat pump as closely as you can to that design, that peak design demand. Because what you don't want to be doing is you don't want to be putting in plant that is oversized. At the very worst case, you could end up short cycling the compressors and actually breaking the compressors or shortening the life of the compressors. So you do want to get that right, and that's why it's important to get this this equation right for getting the peak heat demand. So as I've already said, the absolute ideal scenario. We've designed our house, we've insulated it as well as we can, we've got the ventilation strategy right, so we're not over ventilating, we're not under ventilating, we've got our design heat load. Now we've got to get the heat from the heat pump into the building in the most efficient way possible, and the most efficient way possible is through underfloor heating. So here's our heat pump. We've got a sort of buffer tank sitting down here. And then we've got these underfloor coils, which is actually putting heat out into the building. Obviously, those would be replicated downstairs as well. And we've got our bathroom here, and probably have a domestic hot water cylinder somewhere else. In most cases, with an air source heat pump, actually, you don't need a buffer cylinder, but it's just shown there as for a bit of clarity. So, what are the benefits of underfloor heating? Well, the biggest benefit with an air source heat pump is that you can get the lowest possible flow temperatures, and the lowest possible flow temperatures means the best coefficient of performance. So for every kilowatt hour of electricity you're putting into that heat pump, you're getting the absolute maximum amount of heat out into the house, and that means lower running costs, lower energy bills, happy customers. Next thing is that because underfloor heating actually transmits most of its heat through radiative effects rather than convection effects, you get a greater level of comfort and well-being. There's also some quite interesting diagrams, which I haven't included in here, but a quick Google will bring them up, showing how people's perception of comfort varies with which parts of their body are warm. And most people are most comfortable where their head is slightly cooler than their feet. And obviously having a warm floor helps promote that, and again helps promote that feeling of well-being. because you're not having to put anything on the wall, it gives you the greatest flexibility in terms of layouts. So you can have pieces of furniture pushed right up against walls without affecting the heat output from radiators, etc. So it gives you the greatest flexibility. This is one that people don't often think about, but it's actually quite a good selling point of underfloor. Is that because you're not relying on convective effects, the amount of air and dust movement within the house drops. So that can be quite good if you've got people who've got allergies or particularly sensitive to dust or dust mites. Because you've got less air and dust movement, it can be better for them as well. Also, underfloor heating works very well with flooring that could be considered cold without underfloor heating. So things like ceramic tiles, that kind of thing. And again, those are less likely to trap dust and dirt than say carpets are. So it can be good from that point of view. And it's compatible with most floor finishes. Just obviously a little bit of care when you're using a floor as a heat emitter. If you start putting great big thick highly insulated carpets over the top of it, oddly enough, it tends to keep the heat in the floor rather than letting it out into the room. So the downsides of underfloor, it is expensive to retrofit. The upfront cost actually on new builds is coming down, and although it's slightly more expensive than radiators, when you actually start looking into it in a bit more depth and you start specifying low flow temperature radiators for new build, it actually doesn't work out that much more expensive. So hence why I've made it quite specific to retrofit. And also, underfloor can be quite slow to respond to changes in room temperature, because you're dealing with quite a lot of thermal mass. Even when you tell the underfloor heating to switch off, it will take quite a while for that to cool down, and it will also take quite a while to heat up. Now, that's in of itself is not a problem. Because what you can do is you can set the control system to respond to that. But that's where that sort of idea that, oh, I don't want underfloor in my bedroom because it will make the bedroom too hot. Well, no, we'll just sort of offset when you're going to when you're going to go to bed. Make sure you turn the heating down a good couple of hours before you go to bed to allow the floor just to start cooling down a little bit before you get into bed, and that will allow sort of nice controllable room temperatures. So the sort of other alternative to underfloor heating, and as I said, right back up in the myths section, right at the start of this presentation, we were looking at whether underfloor or radiators could be used, and the answer is both can be used. What we do want to do with radiators is we do want to make sure we keep the flow temperature down. And how do we do that is well, it's obviously so the benefits of radiators are they're easier for retrofit, they're cheaper to install, especially in retrofit situations. They are slightly cheaper to install in new builds, but not by as much as you might think. Obviously, you can have an absolute full choice of floor coverings and finish. Downsides are that because they operate on higher flow temperatures than underfloor heating, you will tend to get a lower coefficient of performance. And because you've got wall space requirements, you will get reduced design flexibility. And the other thing is we're trying to get the flow temperatures down to give us this good COP. Low flow temperature radiators do tend to be more expensive and larger than standard radiators for the same heat output, but you do need those low flow temperature radiators to maximize the benefits of the heat pump. So you've got this slight contradiction there with them being cheaper, but also being potentially more expensive as well. But this is what I was saying with new builds, because you're wanting to spec low flow temperature radiators, it does make underfloor heating more competitive in terms of price. It's still slightly more expensive. Okay, so we've got a very unhappy looking child here with their fingers in their ears, obviously upset about noise. The good news is that a correctly designed and implemented air source heat pump system will not be noisy. Usually, when people complain about the air source heat pump being noisy, What they're actually complaining about is some elements of the design not having been thought out properly. So a good example of that is people installing an air source heat pump in an area where you've got loads of hard surfaces. You get loads of reverberation. There's nothing soft to absorb any noise that the heat pump's making. But actually, they're not noisy at all. If you look on this chart, this is where a heat pump sits. Is right down here. It might not be the easiest thing to read, but we're talking about typically around 40 to 50 decibels for a heat pump. Remember that decibel scale is logarithmic, so doubling the number of decibels is 10 times as noisy. So if we're in a library, we might be expecting to have a sort of background noise level of between 30 and 40 decibels. Your average office at work is probably going to be in the sort of 50 decibel kind of range. Your dishwasher, etc., is going to be noisier than your heat pump. And then when you start, so you're looking at, pretty moderate levels of noise. Now, if you go into a room with no soft furnishings in, and you put a loud, fairly loud sort of ticking clock in there, it'll be quite noticeable because it will reverberate. And the same thing happens with heat pumps, is if you don't site them wisely, then they can appear noisy, but actually they're not. So the first thing to say is noise issues aren't anything like as common as people, some reports suggest. Like with most of these things, you hear about the bad cases, you don't hear about the good ones. It can be heavily managed by using soft surfaces and plants, and by avoiding hard surfaces where you get reverberation. The other thing to remember is noise is directional. So most heat pumps will be noisier directly downstream of the fan. So point the fan away from where you're living. Fairly easy. Most heat pumps are designed so that the intake is on the back of the heat pump, the side that would face the house, and then the front allows the air to dissipate away into the environment. With it, that takes the noise as well. So if you point that heat pump away down the garden towards some planting, away from sort of hard surfaces, then that noise will just disappear. You won't notice it at all. Okay, so that's noise covered. The other big one that can catch people out if they're not careful is electrical supply. Electricity supplies are basically come in sort of two flavors: single phase supply, which is great for installations up to around 15 kilowatt thermal. So that's going to cover the majority of houses. It equates to a house of around 300 meters squared for a new build home. A little bit less than that if it's retrofit, obviously depending on insulation levels. And with a single phase supply, in most cases, there's no requirement for any kind of power upgrade. You would just need to notify your DNO that you're installing an air source heat pump, and the air source heat pump in that case would typically be fed from a dedicated radial circuit from the existing consumer unit. So it's a fairly straightforward electrical installation. When we start getting into bigger heat pumps, and by bigger I'm sort of talking 15 kilowatts plus in terms of thermal output. So obviously you can sort of divide that by so that's about sort of 5 kilowatts electrical input. Then you're really then starting to look at three-phase installations. That will mean that for most domestic properties, you're looking at a power upgrade, and that power upgrade can vary significantly in price. I've seen costs of power upgrades to three-phase that have gone from a couple of £1,000 or even less for people who are lucky and happen to have a three-phase supply relatively nearby, up to over £100,000 for a particularly rural property where there was going to have to be significant upgrade of the local electricity network to bring them a three-phase supply. There are some ways around that in some cases. There is also a sort of third option that sits in the middle here called a split phase supply, and that can often be a cheaper alternative where you've got a sort of a demand that's a bit too much for a single phase supply, but you don't need an absolutely full-on three-phase supply. You might be able to get away with a split phase supply there. That's something to talk about on a sort of project by project basis. So the last sort of little bit is on this specification section is about condensate drainage. So here's our little valent heat pump. You can see it's stood on a sort of two little concrete plinths with a soakaway underneath. And that's because the external unit will always need to have a condensate drain. I mentioned it earlier, but just to give you an idea of the amount of water, we can be talking up to 15 litres of water from a domestic sized heat pump per defrost cycle. Typically, domestic sized heat pumps would probably defrost once an hour. So you could be looking at around 15 to 20 litres per hour in some conditions. Obviously, atmospheric conditions will vary that quite a lot. Generally speaking, on cool, very humid days, you will get a lot of condensate because the heat pump will be working quite hard, and because you'll probably got a very high relative humidity, you'll start getting quite a lot of condensate on the evaporator. Usually, the condensate is simply dealt with a little pipe that runs from the bottom of the heat pump down into a soakaway. But obviously, if you're on very, very heavy ground, you just need to think about, is there actually is the soakaway going to work properly, or do you need to take it to a drain? It's pure water, so there's no problem with connecting it to a drain. The thing to avoid, obviously, is allowing it to drip onto paths or drives. Okay. So now the interesting bit, this is the bit that everybody always likes. How much money are the government going to pay me to have a heat pump installed? Well, the good news is there's a couple of different options, and we're going to concentrate on the domestic options. Commercial RHI is a little bit more involved, so we'll talk. We can talk about that on a project by project basis. But let's have a look at some of the sort of basics here. So the renewable heat incentive. We're going to concentrate on the domestic RHI, but there is also the non-domestic RHI. We're also going to talk a little bit about this, about the new system, which is called the Green Home Grant, which can be used in conjunction with the renewable heat incentive. And then there's two schemes within that, which is the general scheme and the low income scheme. And we'll talk a little bit about those. So the domestic RHI is paid over 7 years for any qualifying installation. And to be a qualifying installation, it basically needs to be installed by an MCS installer and be an MCS accredited product. So the MCS is the Microgeneration Certification Scheme. The payments are designed to reflect the cost of installation over and above that of a conventional boiler system. So the idea is that over the 7 years, you should recoup the additional capital cost that you put in to install your low carbon heat pump. The money is tax free, and there are maximum payments. So if you've got a particularly large home, you'll probably hit these maximums. But for an SOS heat pump, the maximum payment is £10,100 over that 7 year period. And what you do is you as you get an energy performance certificate, an EPC for your home, that will tell you how much they expect you to, how much heat they expect you to use. If your air source heat pump is your only source of heating, you will then just simply get 10.71 pence times the number of kilowatt hours that you're expecting to use each year. It's paid quarterly, and you just get that money back up to a maximum of £10,100. So it's a nice little sort of freebie, and obviously you get the lower running costs of the air source heat pump over a conventional boiler system for the entire life of the system. So it's really free money. And it can be used in conjunction with the Green Homes Grant. And effectively, the way that works, we'll look at on the next slide. So the Green Home Grants is opened in October. But basically, you can get up to £5,000 or 2/3 of the cost of installation on the Green Homes Grant. And then there's the as I said, the low income version, which is the up to £10,000 or the entire cost of the installation. Installers must be MCS certified. So this is the last point, which the one that wanted to pick up. So basically, if you receive the Green Homes grant, effectively the way they do it in conjunction with the RHI is they just look at it as an advance of RHI payments. So it just helps offset that initial capital cost a little bit more. So whilst it doesn't mean you get any more money in the long run, it does hopefully help you finance that initial outlay a little bit better. Okay, so that's the sort of money side of it done. As I say, there's bits about who's eligible, but most property owners are eligible for the Green Home Grant. The only ones that aren't are for those who are building absolutely brand new properties. So it's designed as a retrofit scheme. So let's have a look at some next steps. I'm going to put up 10 considerations that I think, if you remember nothing else about what I've talked about this morning, try and remember these 10 things. Number one, and it's the one that appears in pretty much every mesh presentation: improve the building fabric before designing the heating. Design services in early. We all like to have plenty of space that we can actually fit the equipment in. There's nothing worse than trying to fit an installation into a space that wasn't designed for it. Match the heat pump size and the peak heat demand. Absolutely crucial. Don't want it to be oversized, and equally don't want it to be undersized. Use underfloor heating if possible to maximize the COP, so get that flow temperature down. If we can't use underfloor heating, then low flow temperature radiators. Again, it's all about driving down that flow temperature to get the best COP. When you're siting the external unit, consider the airflow to and from that external unit. The issue I talked about, sort of cold traps and debris traps. Just bear those in mind. And also consider where the noise is going to, anybody that might be affected by the noise from that external unit. It is quite low level noise, but it can be irritating. Check the electrical supply and allow for any upgrade that may be required. Most the DNOs will give you a budget cost for upgrade if it's required for free. Allow for good condensate drainage. And remember that the renewable heat incentive and the Green Home grants are there to help you with financing. That's it. If you remember those 10 things, I'll be very, very happy, and you'll get top marks on your exam at the end. So hopefully that hasn't bamboozled you all too much, and we can now look at some of the ways that we can help you as Mesh. So at the very early stages, we would suggest that we get a feasibility study done as soon as possible, because a feasibility study will tell you whether an air source heat pump is the best technology for your particular project. It may be that a ground source heat pump or some other technology is more suited to your application. We can help with energy and SAP calculations, and we can also help you with doing those initial layout drawings, just getting making sure there's enough space for the equipment to be installed. Then at REBA stage 4, when we're doing a bit more detailed design, we can look at a full specification, do some install recommendations, and do your tender specification. Any of you that want to see a copy of what one of our tender specifications look like, please drop me an email. I'm more than happy to send you out a sort of draft one to show you. Then once the builders are being appointed and specialist contractors are being appointed, we can review tenders that are coming back from people and provide installation oversight. And then finally, post-installation, we would be looking to do energy monitoring, particularly on heat pumps. Poor commissioning can really increase energy costs, so it's quite important that you get that right. Okay. Well, hopefully there's a few that I haven't bored into tears, and there may well be some questions. So if you have any questions, please fire away. Rhiannon, is there anything in the comments?
Okay, sorry about that, David. I was answering the phone.
That's all right.
We do have a couple of questions.
Yeah.
Current chatter is that GHG is oversubscribed and finding approved installer with availability before the pot runs out is almost impossible. Any experience or thoughts on this?
That is certainly an issue with the Green Home Grant as it's being done at the moment. It's a wider issue, I think, generally, in that there simply aren't enough specialist installers to meet the demand at the moment. If I was a qualified plumber, I'd be getting my MCS as quickly as I could, and I'd be making damn sure that I was going out and installing heat pumps, because the demand is absolutely enormous, and it's certainly outstripping supply. So yes, it is an issue. We know it's an issue. Luckily, Mesh have some really good installers that we work closely with, and we try to get them involved with projects early, so they got sort of a good foresight of what's coming, and that certainly helps, because we can sort of get things planned in a fair way in advance. But certainly with the Green Homes Grant, that is an issue.
Okay, question from Helen: what size plant room is required for split unit on a large house?
So depending quite how large, I would say allow at least 4 meters squared internally for the kit. Typically, I mean, if we said that you're going to be allowing, say, 60 liters per person of hot water storage, so say it's a 6-bedroom house, so that'd be maximum occupancy of 7 people on the basis of 1 bedroom, one person per bedroom, except for the master where you have 2. So for a 6-bedroom house, you'd probably be looking at a 500-liter cylinder, and a 500-liter cylinder, off the top of my head, is about 800 millimeters diameter by 1.8 meters tall, and then you'd have the internal air source unit on top of that, which would be about the same size as a gas boiler, can be wall hung. So if you allowed 4 meters squared for all the pipework and gubbins and everything else, so a bit more than you'd have for a gas boiler installation.
Okay, so we've got 2 final questions in the last 2 minutes, or 3 actually.
Yeah.
So briefly, what is the lifespan of an air source heat pump compared to a gas boiler?
So as with any of these things, it's kind of a how long's a piece of string question. But I know of air source heat pumps that are 15 to 20 years old that's still running. There are some things that can reduce the life of an air source heat pump. Short cycling of the compressors can seriously reduce their life. So again, that's down to getting the sizing correct. And also, if you have extremely corrosive environments which can affect the evaporators, that can reduce their life. So installations that are very close to the sea, where saltwater corrosion can be an issue, then there's certain things you can do to the evaporators in terms of treatments to make sure their life of those is as good as possible. And of course, choosing a quality product to start with also helps. So looking for good quality compressors, good quality casings, those kind of things. An awful lot of the heat pumps you see failing, actually it's not the refrigeration side that fails. It's actually often the casings that fail, because they use a low quality steel, and actually that's one of the things you pay for with more expensive brands is the quality of the casings, so they don't rust away.
Okay, could you give a brief bit of overview guidance as to when air source heat pump is better and when ground source heat pump might be better? Okay,
so this is going to be a very much a sort of generalities type of thing, but so air source heat pump tends to suit smaller properties better than ground source, because a lot of the sort of fixed costs of the fixed capital cost of installation of a ground source heat pump can't be made back by its lower running costs. So a ground source heat pump, once it's installed, will have lower running costs than air source heat pump for the same heat output. The disadvantage of ground source heat pump is that it will be more costly to install. That the sort of crossover point, generally speaking, is on houses that are around about that sort of 15-16 kilowatt thermal kind of mark. At that point, it tends to be that's where ground source sort of starts overtaking. Now, there's obviously lots of other bits that other moving parts that go into those equations. So things like land availability, how easy it will be to do the collector installation for ground source, electricity costs, solar PV inputs, all kinds of other things that can all change that equation. But that's a kind of a good starting point. Is anything over about 15 kilowatts plus, ground source is likely to be pretty competitive. Anything below that, it's more likely that air source will be competitive.
Okay, I'm just a bit conscious we run over time, but hopefully 2 quick questions to finish. Can you briefly touch on the suitability of air source heat pump for flat developments? And also, it might tie in quite well, can air source heat pumps give ducted air installation?
So just to pick up on John's question about the ducted air installation, the heat pumps I've been talking about are air to water heat pumps. Air to water heat pumps are eligible for the RHI. Air to air heat pumps do exist. So where you're taking heat out of the air and heating air with that heat. That type of heat pump aren't eligible for the RHI, so we usually tend to steer towards air to water heat pumps. But yes, you can do ducted air installations with heat pumps, but you wouldn't get the RHI on them. In terms of flat developments, air source heat pumps can work quite well for flat developments. Again, it depends on the number of flats and exactly how you want to sort of do the metering and that kind of thing. So there's a couple of ways you can do it. You can either do a very small heat pump for each flat. That can work quite well. The question then is always, where do you put the external units without making the building look a bit ugly? So that's sort of one consideration. But the other way of doing it is a sort of centralized large air source heat pump, and then heat interface units for each flat, and then the sort of bit there is about how do you meter it and make sure that the billing's all done correctly and that kind of thing. So yes, they can be very good for flats, and especially if you're looking at trying to reduce carbon emissions and improve SAPs, then a good option.
Okay, that's it.
Lovely. Well, thank you everybody for coming today, and if you've got any more questions, then please feel free to drop me an email. We're always here to help you. So yeah, great. Thanks very much.